so this will be a bit of review, we hope. Okay. Although sometimes electron configurations are not taught in some of the Chem 1 classes. I don't know if it's in first semester. I think here it's in the second semester. Well, no, it's in the first semester here, yeah, where we go through sort of building up the electronic structure of an atom. So we know the nuclear structure of an atom. That's simple. We got a nucleus, and it's located at some place in space. But what's the electronic structure? You know, what types of electrons do you have? We have those 4 quantum numbers. Each electron has its own set of 4 quantum numbers. It's in a particular principal quantum number, so that would tell you the shell, 1, 2, 3, 4, all the way up. It has an L, which is the angular momentum. That's the orbital that it's in, or that's type of orbital, either an S, a P, a D, an F. The M sub L is the magnetic quantum number. So if you put that atom in a magnetic field, then the orbital angular momentum is kind of like a spinning charge. So it has a magnetic moment. So right-hand rule, if the magnetic field is your thumb, then the right-hand rule would say that the charge follows from X to Y. So it essentially makes a current around that magnetic field. Or if you have a current, if you have a spinning charge, then it produces a magnetic field. So a magnetic field can induce a current, or a current can induce a magnetic field. And so my fingers are sort of the rotating magnetic field, or rotating charge, and the thumb is the magnetic field. And so the electrons in a particular orbit are going to have magnetic fields that align with or against the induced magnetic field. And so that's where the M sub L quantum number comes from. So it's M for magnetic, sub L, meaning it's the orbital angular momentum. So that's the 3rd quantum number. And that's the one that tells you which p orbital you're in. The p0, p plus 1, p minus 1. We typically call those px, py, pz. And then you have the d orbitals. Now you have 5. So you have 5 places that magnetic moment can point. And you see pictures of this in the book. You'll see these little cones. Now the reason they're cones and not particular vectors in space is because we don't know where that magnetic field is. We just know its magnitude against the z-axis, which would be defined as the magnetic axis. So it could be anywhere up, middle, or down. So we don't know in space in the x and y direction where it's pointing, but we know its z direction, how much it's tilted up or tilted down. Same thing with an electron spin. So the intrinsic spin of the electron is, again, like a spinning charge, and it produces a tiny little magnetic moment, and it can be plus 1/2 or minus 1/2. So if you put that in a magnetic field, it's going to be 45 degrees up or 45 degrees down against that magnetic field. So that's the 4 quantum numbers, and every electron in an atom has those 4 quantum numbers. Okay, they're in a particular shell, a particular orbital, and have a particular set of spins. Now, we're going to build up those electron configurations. And now they're configurations and permutations. Those are 2 words that we'll use throughout the course and even into the spring. A configuration doesn't pick which electron is in which orbital. It says there's 1 electron in this type of orbital, 1 electron in that type of orbital. So it doesn't nail down. The permutation would be every possible combination. So putting an electron in the px and 1 in the py, and then a py and a pz, or the px and the pz. Those individual things are called permutations. For electron configuration, we just say p2. There's 2 electrons in the p shell, or p subshell. And so we're not saying which individual orbital those 2 electrons are in. We will figure out how many combinations there are, but we won't define which tiny little permutation there is. It'd be like saying you're going to flip a coin and you're going to calculate the probabilities of, say, 2 heads and a tail. You don't care whether it was the first 2 flips, the first and the last, or the last 2 flips were the 2 heads. Okay? The particular sequence would be a permutation, but the configuration would be 2 heads and a tail. Okay? So the general result. And so that's what electron configurations are. That's what that word configuration means. It's the general result for the electron cloud. So carbon, if you look at carbon, it's a 1s2, 2s2, 2p2. We don't care which particular p orbitals those two electrons are in. They could be in the pxpy, pypz, or pxpz. Okay, and so that's the electron configuration is 1s2, 2s2, 2p2. So let's learn about these configurations today. So these are the hydrogenic energy levels. There is no energy dependence upon the L quantum number when you just have one electron. But when you go into multiple electrons, then you start to see a drop in energy with those subshells. So notice the difference between this chart. We have the n equals 1 shell here, n equals 2, so that'd be the 2s and the 2p, and the next would be 3s, 3p, 3d. See how the 3s, 3p, and 3d all have the same energy. That would be the hydrogenic system. When you move into multiple electrons, then you start to have energy differences for those subshells. So this is the system that we're going to use. This is for multi-electron atoms. And you have the 1s, the 2s, the 2p. And so what used to be here in the hydrogenic system is now moved up a little bit. Okay? And then the 3s is here, and the 3p is there, and the 3d is there. The ramifications of this is that they fall in typical order until you get to the 3D, and the 4s is lower in energy than the 3D. And so that's why when we're filling these, we don't fill up the full 3 shell before we go into the 4. We put the 2 electrons in the 4s before we get to the 3D, and it's totally based on these energies. So we're putting the electrons in the lowest energy setup. So we're by nature, we're making the electron configurations for the ground state atom. You could have that first electron for potassium be in the 3D shell, but that would not be the ground state potassium. Okay, that would be an excited state potassium. And you can have excited potassium. You can put that electron in there, but if you wait long enough, it's going to spit out a photon of light and drop down to the 4s, and then you'll reach the ground state potassium atom. And so this is where our electron configurations come from. And we can look at the periodic table, and we can see, hydrogen 1s1 is that first electron. It goes into the 1s orbital. That's easy. Helium 1s2. Okay, so now why is helium all the way over there and not right here? Well, because it's also a noble gas. And those noble gases typically have a filled electron cloud up to 8 electrons, or 18 when you get to the D block. And so because it's a noble gas, we put helium way over to the right. But that's the end of the 1s shell. We can't have a 1p because the angular momentum quantum number L is bounded by n minus 1. So we can't get up to L equals 1 because n is equal to 1. So the highest L is L equals 0, and that's an s orbital. So you can go back and review why we don't have a 1p set of orbitals. So once we get to 1s2, that orbital, that shell is filled. And we have to go up to the next principal quantum number, n equals 2. So let's jump ahead. Let's do nitrogen. So we find that on the periodic table. We see that it has 7 electrons because it has 7 protons. So the neutral atom has as many electrons as it has protons. So you can just look at the atomic number, n equals 7. Okay. For nitrogen, the atomic number is 7, and so you know it has 7 electrons. So we're going to start with a 1s2 and build all the way up until we get to 7 electrons. And so we have 1s2, 2s2, and then we have 3 left over. We put those in the 2p. And so when you add up the electrons, that's when you know to stop, because we've reached the atomic number of nitrogen. You can also look at the periodic table. You see hydrogen, helium, that's 2. Lithium, beryllium, that's 2 more. And you realize that that's the 2s, 3s, 4s. This is the s block. So when we get past here, we get to beryllium. That's the 2s, the second electron in the 2s. And then you get to the p block over here, p1, p2, p3. So you could just look at nitrogen and know that you're on row 2, third one in the p block, it's going to be p3. So you can check your work against the periodic table. And so if you learn these electron configurations and keep comparing them to the periodic table, then you've essentially got the whole system right there in front of you anytime you have a periodic table. Let's do oxygen. So just look at oxygen's place in the periodic table. It's 1, 2, 3, 4 in the P block. What row is it on? Row 2. So it's going to end up with 2p4, and then you just build your way up to that. So that's going to be 1s2, 2s2, 2p4. So that's oxygen. Now let's talk about energetics. When we get to chromium, we're now in the 3D block. Okay, so we filled up the 1s1 and 2, 2s2, 2p6 gets us to neon, 3s2, 3p6 gets us to argon, then 4s2, potassium, calcium, and then we have 3D, starting with scandium, 3D1, 2, 3, and 4. And so that's what you might expect for chromium, but chromium's a little different. Let me go ahead and fill in these electrons for chromium. So we're gonna use this chart. We're gonna say, all right, there's 2 electrons in the 1s, 2 and 2s. Fill up the 2p, 3s, so that gets us to sodium and magnesium. Then we do the second row of the p block. Actually, you should fill them like this, where you put them all in unpaired, and then you start to pair them up. Okay, so that gets us over to argon. So this piece right here, we'll go ahead and I'm going to do a little thing where we surround this whole block, and that's equal to what we call the argon core. And you can write that down here. You could say argon core. Anytime you reach a noble gas, you could just say, all right, we're going to say the core of that noble gas. That's all the electrons in that noble gas. And then you have the valence electrons. So then we have the 4s, 1 and 2, and then the 3d4. 1, 2, 3, 4. But look here. We've got an open spot here that would have an independent view of the nucleus. So each of these orbitals are in different directions from the nucleus. And we have 2 electrons in the 4s. They're crammed in the same orbital. So if I pull 1 out of that 4s and put it in the 3D, now the 4s electron has its own independent view of the nucleus. And all 5 of my d orbital electrons have their independent view of the nucleus. And the whole atom drops in energy. And so that's going to be the ground state for chromium. Whenever we get close enough to that half-filled subshell, we have an opportunity for every electron to have their own independent view of the nucleus. So that's why half-filled subshells are stable, because every electron has got its own way to interact with the nucleus. It's in a slightly different direction. And so this is a possibility for chromium. It's just not the ground state. So if we move that electron over, then it drops in energy, and we do have the ground state chromium. So I'm going to scratch this one out and move it over here. And so now what we call an exception to the Aufbau filling scheme, we have that 4s electron moving over to the 3D, and now we have 4s1, 3d5. So that would be the ground state electron configuration for chromium. So 4s1, 3d5. And you see that S1 is a half filled and the 3d5 is a half filled. Everybody, I see a few nods occasionally, so that you've seen this before, but it's maybe not had it explained with the energy level diagram. So what we're looking at is we're looking for the ground state of that atom, and this is a valid electron configuration that has lower energy than the other one, where you had a 4s2, 3d4. Okay, you can look at this, and you could say, well, what about molybdenum? So let's take what we've just learned with chromium and do molybdenum. Okay, let's try to make it easy on ourselves. So here's molybdenum, it's number 42. I really don't want to count up 42 electrons. Okay, so I'm going to go to the previous noble gas. So I'm just going to work my way backwards. Rubidium's 37. So then krypton is 36. So we'll do the krypton core. So let's do molybdenum up here. So Kr, so the krypton core, and then we come over here to rubidium. And so since I've done the krypton core, I need to know what S I'm dealing with. And so that's where these numbers really come in handy. That's a 5, that's the 5th row, so that's 5s. So that gets me back into the scheme so I know what principal quantum number I'm dealing with. So that's going to be 5s1. And then when I go into the D block, it drops down a number. So that's the 4d set, 4d5. You see how similar it is to chromium. It's in a chromium group. So compare those two. Molybdenum up there, 5s1, 4d5. And then chromium is 4s1, 3d5. Yes?
So tungsten do the same thing?
Yes, tungsten will be the same thing. Yep. And then it will be 6s1, 5d5. And then down here, Seaborgium. Did you know that? Seaborg, discoverer of plutonium. Okay. Seaborgium. At this point, I would say do it the same way for Seaborgium. Although when you get down into the lanthanides and actinides and the F block, some crazy things can happen. But in terms of deciding what the ground state, I would actually have to look that ground state up just to make sure it follows this trend. But at this point, if I were to give you Seaborgium, you'd do it this same way. You would go back to the radon core, and then you would do 7s1, and then you have to figure out what the F block is. Yeah, so this would be the 4f block on this row. This would be the 5f block here. So 5f14, there's 14 electrons in the F block. And then this would be the 6d5. So that'd probably be, I mean, that's as far down as we can go. At least today, okay? Who knows if we'll find an 8th row in the periodic table. I suspect not, but you know. I also didn't think we'd ever get to element 118, which is at the very end. Okay. So this is that Aufbau filling scheme, and this is what we've been talking about, that half-filled subshells. And so we say that half-filled subshells are stable, but we haven't really shown you the evidence. And for the spectroscopy material, I was always saying, you know, start with the data. This time we didn't start with the data, so let's go look at the data. So what evidence do we have for this? Okay, this is the first ionization energies. So that's one of your vocabulary words. What is the first ionization energy? So you need to know, this is the data where we get these claims that half-filled subshells are stable and so on. This is the energy it takes to pull one electron from the atom. So that's why we mean the first ionization energy. You're pulling one electron from the neutral atom. And so up here we have the energy of the cation and the energy of the neutral. And so another way you think about this too is you've got, you know, the light coming, hitting the atom, and then that electron's coming off. Okay. And so you could measure the binding energy of that electron. You could also measure the difference in energy between those two. So we could do this with spectroscopy. We could figure out what that energy difference is between the neutral and the cation. So tell me what you see here. I mean, what are some observations? So this is the data. I want the class to kind of point out some things. So we'll just go around. If you see something here that you want to point out, then raise your hand and we'll see what you've got.
Noble gases have the highest.
Very good. So look at the highest ones. The most difficult to pull an electron off is the noble gas. So one of the trends you can pull from that is that a full shell is stable if it takes that much energy to break it. So as we add electrons in, we get to a nice full shell, and it's difficult to break that full shell. So noble gas configurations are stable. They're the highest ionization energies in a particular row. So look, if you go across the row, you get to that noble gas. It's got the highest one in that row. Donovan?
The P1 electrons have some of the lowest. energy.
The P1s, yeah. So here's
Boron, aluminum.
yeah. So here's a P1: boron, aluminum, gallium, indium. Yeah. So we can go down there: boron, aluminum, gallium, indium. There's something. It's easier to pull that electron out than it was the previous electron. Okay. So there's two things you could pull, two trends or two statements you could make from that data point. Okay. So who wants to take a stab at some of the reasons or claims you might make because of boron, aluminum, gallium, or indium? Do you have one that you want to say? Okay.
Yeah. By removing that electron, you still have a full s orbital.
Okay. Yeah. So that you're going one past a full subshell, because S would be a subshell, P would be a subshell, D would be a subshell. So the shell is the principal quantum number. Like n equals 3, that would be the n equals 3 shell. The S, the P, and the D would be subshells. So we go past a full subshell, it's easier to pull that electron off. That's a good observation. Anyone else? Yes. Marcus, right?
Yes.
Okay.
The group 1 elements are also some of the lowest.
Yeah, so group 1, your alkali metals, also very easy. And they are past a filled subshell. In fact, past a full shell filled, the noble gas. So they're one past that. So it's easy to pull that extra electron out. So that you could say either it's easy to pull that electron out, or the previous one's so stable that you're getting back to a really stable electron cloud. So we could try to think about which one of these is more stable, which one of these is less stable, you know, and looking at our energy level diagram. So we'll analyze these individual trends. There's probably one more I've got circled that's a little unusual.
Transition metals.
Transition metals. Okay, what about the transition metals?
It seems like it's almost.
So these would be the transition metals right here. So that's the 3D group. This is the 4D group. And then here's the long run of 5D. And then we get into the 4Fs, which are kind of strange. So let's see, mercury, yeah. No, these are the F block, the 4F block. And then these are the transition metals. There. And then the 5F, I don't know, it's kind of radon. Yeah, we don't even have those on here, so. Well, we got the 4F on there. So what are we going to say about the D blocks, the transition metals?
I don't know how to put it in the word properly. That's what I'm.
Okay.
On. But it seems like if you go into the prior elements, there's a high drop or high
Yeah.
electrical drop in this high distinction.
Right.
But as you go to transition metal, there is no real distinction. It's just a steady climb. Is that what you're talking about? Whenever it says it wants to reach the shelf, it wants to reach the lowest energy. Yeah, thank you.
Yeah.
So that's when it starts splitting with ones and ones and ones and ones. That's why it looks. Is that why you really can't distinguish between each level?
Yeah, there's really not much difference through this whole series of 10. You know, it's pretty gradual. They do increase. Now, if you think about, that may be a trend that you do see, though, in that 3D. They do increase. It's gradual, but they do increase. Notice how going from left to right, they almost always increase. We do see some zigzags, but in general, going from left to right, lithium to neon, all the way across, they increase. Going from potassium to krypton, potassium to krypton, all the way across, they do increase. There are some zigzags, but there's a general trend. Now, let me explain that one. What are you doing as you step across the periodic table? Each step, you're adding two things in an atom. You're adding a nucleus piece, you're adding a proton, and you need to throw in some neutrons to hold the nucleus together. But they don't really play a role in the electrostatics, so they're not charged. So the neutrons are just there to hold the protons together. So you add a proton, which has a charge, and you add an electron, which has a charge. Why is it not straight across? Because you're adding one positive charge, one negative charge. The size, let's see. That's a good question, actually. Are you increasing the cloud much by adding another electron? This is the trend that's kind of speaking against that. It might increase the size, but each electron, because we have different orbitals in different directions, it has its own independent view of the nucleus. It leads up to half-filled subshells. So you're not really increasing the size of the cloud much, but you are adding another positive charge. So all the electrons feel a more positive nucleus. So because each electron feels a stronger pull to the nucleus, it's harder to pull any one of those electrons away. So as you add a positive charge and a negative charge, all the negative charges get pulled a little closer, and it gets harder to pull one of them off. Think about that. As we go from left to right, it gets harder to ionize. So we put one more proton on there, and all the electrons get sucked in a little bit. So actually the cloud gets smaller going from left to right because those electrons aren't shielding the nucleus very well. Now when we get to an N, we change ends, we go to the next subshell, then we do have a jump in size. And so when we go from noble gas over here to alkali metal, we see a jump in the electron cloud size. And so that 3s electron is much further away from the nucleus than all of the other electrons on the inside. And so it's very easy to pull those alkali metals off. Those are the lowest ionization energies because they're farthest away from the nucleus. It's that extra electron that's the furthest away from the nucleus, easy to remove. So let's look at this in detail. Let's look at all of these little trends. So here's some trends. Y'all did a great job. I think you got almost all of them. So trend 1, first ionization energy decreases with the size of the atom. Okay. So if this atom is big, it's a low first ionization energy. Think of the alkali metals. So we go to the next subshell or the next shell, and that's a big atom, so the low ionization energy. Trend 2, first ionization energy increases across the row. We identified that. As we go across the row, the energies creep up. Okay. And that's kind of the same trend. The cloud's getting smaller because we're adding more and more positive charges. Trend 3, the first ionization energy is unusually high from fully filled subshells. So that's like the beryllium group. And so it's got a little bit higher ionization energy than you would predict. Trend 4, the first ionization energy is unusually high from half-filled subshells. Now we didn't notice that one, but that's between nitrogen and oxygen. So we'll look at that one too. We get to a half-filled subshell and it's unusually high to remove that half-filled electron. So nitrogen has an unusually high ionization potential and oxygen has an unusually low one. So all of these are unusually low. From a subshell with only one electron in it, that would be this S1 group, the D1 group, the P1 group. Those are unusually low because it's one electron past being half-filled or fully filled. So let's look at all of these trends individually. So we'll find them in the data. So here's the data. So first ionization energy decreases with the size of the atom. So look at this one. These are the noble gases. We'll just pick those since they're on top and easy to see. Helium's the smallest. And notice how the ionization energy is decreasing and radon's much larger than helium. When we said hydrogen, if the ball at target was hydrogen, our 1s electron was around Navasota or Spring, Livingston, Madisonville, and then the 3s electron in sodium was down in Argentina. Okay, so much larger, so it's easier to ionize sodium than it is to ionize hydrogen. So it's just farther away from the nucleus and easier to remove. Let's look at this now. The ionization energy increases across a row in a periodic table. So which trend is that? Let's just pick sodium through argon. This is a row across the periodic table, and ionization energy increases across that row. We have lithium through neon. So this is an enormous trend. See how steep it is. So across the row of the periodic table, the ionization energy increases. Those are the general trends. As the size gets bigger, it's easier to ionize. You go across the row in a periodic table, the ionization energy goes up. I mean, we kind of drew this probably in freshman chemistry. You said ionization energy is high for helium, and so if you're going up or over, it's getting higher. Okay, and then this would be the easiest to ionize down in this area, francium or cesium. Okay. But now let's look at this fully filled subshell. That first ionization energy is unusually high from a fully filled subshell. We have this noble gas here, but let's just have some fun and do zinc. Okay, so zinc so the lower energy level we have zinc, the higher energy level we have zinc cation. And so this, I'll draw this under the, and call this expected. So we would have an expected ionization trend if we just drew a linear fit to this data, like we went straight across with a line, and zinc would be above that line. It would be higher than expected. That's what we mean by unusual. Okay, we have a trend that would define what usual behavior is, and zinc is unusual. It's too high. It's higher than that. So what can we claim about this? There's two ways to get that arrow to be longer. Okay, we have two energy levels. We can move one of them. Okay, we could actually move both, but we'll just say we were going to move one of them to make that arrow longer. We could move the cation level up, or we could move the neutral arrow down. Okay, moving the cation up would say that the cation is unstable, right? It's got a higher energy. Moving the neutral down would mean that the neutral atom is more stable, because if it's lower in energy, it's more stable. Okay, so what we're saying when we say that fully filled subshells are more stable is essentially moving that neutral energy level down. So this is where the claim comes from, that fully filled subshells are more stable. This goes down to here, and now my arrow is longer than I expected. And we say because fully filled subshell is stable. So do you see how we interpret the data? We look at the data, we have a trend, and we say, wow, zinc is higher than normal. It's harder to ionize than we'd expect. And so the information that we pull out of that is that the neutrals for fully filled subshells ought to be more stable than we expect. Okay? And so since the neutral dropped, we have a harder time ionizing that. Let's look at the next trend. The first ionization energy is unusually high from a half-filled subshell. So let's look at this one here. We're going from carbon, nitrogen, oxygen. What's the next one? Fluorine, okay, and neon. And so if we drew a line straight from carbon to fluorine, nitrogen's above that line. So we have N plus and N. This is what it's expected. and we can drop the neutral or raise the cation, and it looks like, again, we've got a half-filled subshell. We can make that arrow longer if we drop the nitrogen. So it's unusually high for nitrogen. And we could say this dropped down, or the neutral was stabilized because half-filled subshells are stable. So I know you've probably memorized those reasons, those trends, but here's the data, and this is how we came up with those trends. So we're making those claims based upon the data that we see. And this is important because all of chemistry comes from the cloud of electrons. So understanding the stability of the electron clouds and how electrons interact in these orbitals is helping us understand the chemistry. So that's why we get into the details like this. Now let's see if this same idea that the neutral being stabilized holds for the unusually low ionization energies. Okay, so we've kind of taken the data for the unusually high ionization energies, and we've now made a claim that half-filled subshells are stable, fully filled subshells are stable. So those are two claims that we pulled from the unusually high data points. Let's see if that same answer can explain the unusually low ones. So this will be support for the two claims we've made. We've made that fully filled subshells are stable and half-filled subshells are stable. Now, if we do the unusually low ones and we have to change our argument, then there's a problem. Right? But if we get the same argument from the unusually low ones, then it's supported twice. So let's look now. The first ionization energy is unusually low from a subshell with only one electron in it. So a subshell with only one electron in it. Let's go to this gallium example. So we did zinc. Let's look at gallium. So this is expected here. And we have gallium plus and gallium neutral here. And we're saying now that it's unusually low, so the arrow is shorter than we expect. Now, how can we make the arrow shorter? We can raise the neutral or lower the cation. Well, the cation is got the zinc electron configuration. And so if that electron configuration is low, then that's going to shorten the arrow. Same argument. Because that electron configuration is a fully filled subshell. So this time the cation drops. And our arrow is shorter than we expect. And that's because, fully filled subshells are stable. Now we could do the same thing for oxygen. If we do oxygen, let me just do it on the board since I'm out of room. Let me flip over here too. All right. So we have the expected ionization energy, but we realize it's smaller than that. It's easier to ionize oxygen than we expect. And so we need to make that arrow shorter. If we recognize that oxygen cation has the same electron configuration as nitrogen, and it's stable, then the cation has dropped because half-filled are stable. And so let me put the oxygen here. This may make a point too that I didn't state earlier. You know, you don't have to do the electron configuration just for the neutral atom. You need to know how to do the electron configuration for things like oxygen cation. So let's just make sure we understand how to do that. Oxygen cation, so it's an oxygen with one less electron. So look up there. Oxygen has got 8 protons, but oxygen cation only has 7 electrons. So that's going to be going back to the helium core, and then comes in at 2s2, 2p3. That's a half-filled subshell. That's exactly the same as neutral nitrogen. And so you can look at oxygen cation and say, I've got 1 fewer electron, so it's going to be just like nitrogen. If it's 1 less, it moves to the left 1. And so O plus will have the electron configuration of nitrogen neutral. What about O minus? Just look up there and see what neutral atom is going to be, and here's a new term, isoelectronic. Isoelectronic with O minus.
Fluorine.
Fluorine, yeah. So O minus is isoelectronic with fluorine. So let me write that out. I'll do the plus one since it's applicable to what's on the board. O plus is isoelectronic with nitrogen. Has the same electron configuration. Now when we get to our diatomics and molecular orbital theory, we're going to talk about isoelectronic there as well. Okay. And so we'll be putting cations and anions together and making diatomics. Okay. Any ideas or any questions or confusion about this? What are your responses? Is it nice to have a little review? Hopefully it's nice to look at the data behind the claims. You know, we say that half-filled subshells are stable, but this is where that statement comes from. It comes from ionization energy. All right, so see you next time.